Hey, Mr. Martin back with the second video in our series, The Calculus of Transcendental Functions. This one covers the exponential function. In general, we have a function y equals a to the x. We should put a disclaimer. A is just greater than 1. Can't be 0, can't be 1, cannot be negative. You can generally show that if you have a to a function, then the derivative is a to that. This should be f of x. Times ln a times f prime of x. We'll come back to that one. We use this rule to establish a baseline for Euler's number. If we have y equals e to the x, then its derivative is itself. Now this makes sense if we think about what it means for something to grow exponentially, then the rate of change should also be exponential. That is indeed what happens with the exponential function. Generalizing it a bit more, if we have y equals e to some function, then its derivative is equal to e to that same function multiplied by the derivative of the exponent. This thing is the derivative of the exponent. The examples of this are pretty straightforward. We will just continually apply this rule. Be mindful that the product, quotient, and chain rule always apply if needed to find that derivative. So for example, A, we would get y prime equals e to the 3x squared, and we never change the exponent, so we just multiply by the derivative, which is 6x. If we wanted to reorganize this, it would be 6x e to the 3x squared. That's it. For letter B, we would get y prime equals, the derivative of the sine is cosine, and we never change the angle, so that's going to be cosine e to the x cubed, and then we multiply by the derivative of the angle, which is e to the x cubed times multiplied by the derivative of the exponent is 3x squared. Rewrite would give us 3x squared e to the x cubed times cosine e to the x cubed. Notice, again, we did the derivative of sine, which is cosine, never change the angle, multiplied by the derivative of the angle, which is that. Letter C, we have y equals x squared plus 10 times e to the negative 2x plus 1. This is a case where we would have to do the product rule. So this is our 1, and that's our 2. So the product rule is 1 d2 plus 2 d1. So the first function is x squared, you know what, label, y prime equals x squared plus 10 times the derivative of e to the negative 2x plus 1, which is e to the negative 2x plus 1 times negative 2 plus the second function is e to the negative 2x plus 1 multiplied by the derivative of x squared plus 10, which is just 2x. So if we simplify this, we would get, we'll put the e in the front, so e to the negative 2x plus 1. Oh, I forgot the negative 2 here, so negative 2 e to the negative 2x plus 1 times x squared plus 10 plus 2x e to the negative 2x plus 1. If we wanted to, we could take out a common factor of negative 2 e to the negative 2x plus 1, but we will not. Letter D, we have 3 plus e to the x divided by 3 minus e to the negative x. This is a situation for which we would need the quotient rule. So remember, quotient rule is low d high minus high d low over low squared. So let's see, g prime of x equals, the low function is 3 minus e to the negative x, and then the derivative of the top is, well, the derivative of 3 is 0, the derivative of e to the x is just e to the x. So minus the high function is 3 plus e to the x times the derivative of the bottom, which would be 0 times negative e to the negative x times negative 1, which effectively makes that a positive 1. So all of that divided by 3 minus e to the negative x squared. You should simplify on the top. We would get 3 e to the x. E to the x times e to the negative x is going to be e to the 0, so minus 1, minus another 3 e to the negative x, and e to the x times e to the negative x is, again, 1 times the negative, so minus 1 over 3 minus e to the negative x squared, which if we fully simplify, we would get 3e to the x minus 3e to the negative x minus 2 over 3 minus e to the negative x quantity squared. For example E, we have to find dy over dx, and notice we have the x and the y mixed with each other, so we'll have to do implicit. Imagine that we already applied our derivative operator. So we would get e to the xy times the derivative of the exponent, which requires the product rule. If we derive xy, we will get the derivative of x, which is 1, times y, plus the derivative of y times x. So that's going to give us, we'll put it in a different order. We'll say x dy over dx plus y, then plus the derivative of x is 2x minus 2y dy over dx. Oh, you know what? Make this, I don't know, equal 7. So that equals 0. I guess it's prudent to distribute e to the xy, so we get x e to the xy dy over dx plus y e to the xy plus 2x minus 2y dy over dx equals 0. We'll add, let's see, move the y e to the xy and 2x to the other side, and factor out dy over dx to achieve dy over dx times x e to the xy minus 2y equals negative 2x minus y e to the xy. Our next step is going to be to divide by x e to the xy minus 2y, so we get dy over dx equals negative 2x minus y e to the xy divided by x e to the xy minus 2y. Sorry, lights went out. So moving ahead, if we go back to the original rule that we had, for example F, we have 7 to the x. So we have this rule: if y equals some number to the x, its derivative is that same number to the x times the ln of that number. That would make the derivative here, y prime equals 7 to the x times the ln of 7. That's it. For example G, we're going to have 11 to the 2x minus x squared. We multiply by the derivative of the exponent, which is 2 minus 2x. We multiply by the natural logarithm of the base, which would be the ln of 11. That's it. So for h, we need to find the equation of the tangent line for y equals e to the 2x divided by e to the 2x plus 1 when x is 0. First, we should find our y. So the y when x is 0 is going to be e to the 2 times 0 over e to the 2 times 0 plus 1, which that's 1 divided by 1 plus 1, which equals half. So the point that we have in question is 0, 1 half. The next thing we need to find the equation of the tangent line is the slope. So we will get y prime equals quotient rule again. So low function e to the 2x plus 1 times e to the 2x times 2 minus the high function, which is e to the 2x, times the derivative of the bottom, which is e to the 2x times 2, all divided by e to the 2x plus 1 squared. And if we evaluate this derivative at 0 to get our slope, anything to the 0, so when we substitute in 0 for x, we'll get this entire exponent to be 0. So it's going to be 1 plus 1 times 1 times 2. All right, let's just write it out. We'll get e to the 0 plus 1 times e to the 0 times 2 minus e to the 0 times e to the 0 times 2, all divided by e to the 0 plus 1 squared. So 1 plus 1 times 1 times 2 is 4 minus 2 over 1 plus 1 is 2 squared is 4. So we end up with 2 over 4, which equals a half. So our slope is a half and our point is 0, 1 half. So the equation of the tangent line is y minus 1 half equals 1 half times x minus 0. And last is I. Determine the critical values for y equals e to the x times x squared plus 1. So to determine critical values, we need the first derivative. The first derivative requires the product rule, so we'll have e to the x times the derivative of x squared plus 1, which is 2x, plus x squared plus 1 times the derivative of e to the x, which is still e to the x. The critical values will be the places where this equals 0. Our recommendation is first we take out the common factor of e to the x. So we get e to the x times, that will leave us with, we can rearrange this and get x squared plus 2x plus 1, and that equals 0. So the first thing we should notice is this is a perfect square trinomial, which simplifies to be e to the x, and this would be x plus 1 squared equals 0. So the two things that could happen, either e to the x equals 0 or x plus 1 squared equals 0. This one has no solution. E is a positive number. You cannot raise it to an exponent and get 0. So this is no solution. This other one is obvious, x equals -1. So the only critical value we have is x equals -1. Alright guys, that concludes this video over exponential functions and their derivatives. Everything that we can do with derivatives such as points of inflection, relative maximum and minimum, increasing and decreasing, concave up and concave down, and equations of tangent lines, we can also do with exponential functions. That is practice that we will do in class.